Hello and welcome to our webinar today with the topic of vacuum basics and rotary evaporation. But before we start, I would like to introduce myself. My name is Florian Heinrich and I have been a product manager at Vacuumbrand for 2 years now. About my educational background, I studied chemistry and then also did my PhD in the field of organic chemistry. During this time, I was able to obtain a lot of practical experience with the rotary evaporator in the everyday laboratory work, and so have also a very close relation to this specific application. Let's have a quick look through the agenda for this webinar today. We start with a short chapter on vacuum basics and then move on to the main topic, the rotary evaporator. Here we start with the basics of how it is set up and how it works, before we move on to the optimum process conditions and finish with a best practice example. As you would expect it for a chapter called Vacuum Basics, we will start with a historical overview. In 1644, the first man-made vacuum was created by the scientist Evangelista Torricelli with the help of a column of mercury in a curved glass tube. He is therefore also the inventor of the mercury barometer. And the name gives it away, a physical unit of measurement is also named after Torricelli, the torr. But at this time, this man-made vacuum was only an experiment without any scientific proof. But shortly after, in 1647, Mr. Blaise Pascal followed up with more experiments. He clarified the concepts of pressure and vacuum by generalizing the work of Evangelista Torricelli. Therefore, Mr. Pascal was able to prove for the first time in history that a vacuum can actually exist. Also, the official SI unit for pressure is named after him, Pascal. To make vacuum popular and bring it to the public, Mr. Otto von Guericke played a very important role here. In 1657, he started with spectacular experiments. For example, he hitched 16 horses at 2 metal hemispheres from which he had previously evacuated all the air inside. 8 horses on each side. And the audience was amazed when the horses, with all their power, failed to separate these 2 hemispheres. Only afterwards, when he just opened the venting valve, he vented the metal ball and the 2 metal hemispheres just fell apart without any pressure. And of course, for us, the company of Vacuumbrand, it is very important. A very important date in history is in 1982. Then here Vacuumbrand introduced the first chemical-resistant diaphragm pump that revolutionized the work in the chemical laboratory ever since. Now to the definition. If we ask ourselves the question, what is a vacuum? The answer seems to be very complicated. But in simple terms, we can define vacuum as a pressure below normal atmospheric pressure, or if the pressure is lower than 300 millibars. So it is lower than the lowest atmospheric pressure on the Earth's surface. And the atmospheric pressure, on the other hand, depends largely on 2 factors. The altitude. On this picture, we can see at a level of 5,500 meters above sea, we only have around 500 millibar of atmospheric pressure, which is already half the atmospheric pressure we are used to. And the second factor is the air pressure. So, in the next section, we take a closer look at the various vacuum levels in the laboratory environment. Understanding the vacuum ranges is the key to selecting the right vacuum pump for your individual needs. So we have this little graph here. The most important pressure ranges can be divided into the rough vacuum, the fine vacuum, the high vacuum, and the ultra high vacuum. Depending on the respective pressure range, different pump technologies are used to generate the vacuum. In the so-called ref vacuum, from atmospheric pressure to 1 millibar, we find the most important applications for a chemist, such as filtration, evaporation, distillation, drying processes, and so also the rotary evaporation. Water jet pumps and diaphragm pumps are the most common technologies here. In a fine vacuum, from 1 millibar down to the 10 to the minus 3 millibar, we find applications such as the Schlenkline, freeze drying, and molecular distillations. But also analytical applications start here. Rotary vane pumps, scroll pumps, and screw pumps are the most common technologies in this vacuum range. In high vacuum, we mainly find applications in the field of physics and analytics. Therefore, turbomolecular pumps, I would say, are the most common technology here. And to summarize, the rough and fine vacuum ranges are the most important for the chemical laboratories. And the high vacuum is mainly found in physical and analytical laboratories. So, what is actually the right vacuum for my application? And why is it so important to select the right vacuum pump from the beginning? We have prepared a small experiment to answer these questions. Therefore, we now switch to our test laboratory, where we filmed a little movie, and here we go. So, what did we just see? To start with, we ran a filtration with an oil pump. So we used a very, very strong vacuum. More power is always better, right? But what did actually happen? The filtrate started boiling and foaming, and the filtration just dripped. We saw evaporation instead of filtration. So we had a far too strong vacuum for this kind of filtration setup. This can lead to a lot of problems besides the heavy foaming, like damage to the filter. It therefore may harm the sample, or can lead to pump damages, as the chemical vapor will just pass directly into the pump. In the second run you saw, with the appropriate vacuum required for the filtration, most likely around 100 millibar, we had a perfect filtration run, and that in a safe manner. So no damage to the sample or the pump. In conclusion, it's not always correct to state the more the better. It's about selecting the right vacuum for your application, and therefore also the right vacuum pump that serves this range. Now we move on to the main topic of this webinar, the rotary evaporator. In general, rotary evaporation is perhaps the most common application for vacuum technology in the lab. And in this chapter, I will guide you through the entire process of vacuum evaporation, starting with the general setup and then ending with the optimal process handling. Here we can see the classic design of a rotary evaporator. At the bottom we have the heating bath. Here the temperature can be set via the control panel, and the control panel can also be used to set up the rotation speed of the evaporator flask we see above. So these were the components on the evaporation side, and here marked in red. The blue side on the left is then the condensation side. Here there's also the condenser and the corresponding collection flask underneath. Let us now look at the general function of the rotary evaporator. First of all, for that we need to think about the right choice of evaporator flask. In order to obtain the highest possible surface area, the evaporation flask should not be filled to a high degree. The size of the flask should be chosen accordingly. It is most common to fill like half of the flask here to ensure that you have a very large surface area for evaporation. Now, after we chose the right flask, we can start with the application. Due to the rotation of the flask, a very thin film of solvent forms in the inner surface of the flask, resulting in a very high evaporation surface. This increases the evaporation rate and so shortens also the whole process time. The evaporation creates a slightly overpressure in this flask during this part. And while the condensation of the vapor in the glass cooler, so on the blue side, on the other hand, creates a negative pressure there. And therefore, the condenser acts like a mini vacuum pump. This means that we have a pressure difference that is created between evaporation and condensation, and this pressure difference is the driving force and responsible for the vapor transport from the flask to the cooler. And this is automatically happening when using a vacuum pump. So, the evaporated solvent then starts to condensate at the glass cooler and flows into the collecting flask. The job of the vacuum pump is now to establish and maintain the process pressure and, if necessary, also to adjust the process pressure to the new distillation conditions. It is important that the rotary evaporator operates in equilibrium as much as possible. But what does it actually mean? But very simple, this means that the evaporation and the condensation capacities, so the processes, should be as equal as possible, and then we have a good equilibrium. But I will come to that in more detail later in this presentation. Now, where's the rotary evaporator usually used? The rotary evaporator is a very simple distillation device. It is applied for the evaporation of solvents, for sample concentrations, simple distillation runs, and also for drying purposes, as well as for recycling and purification of solvents. So a broad range of possible application use. And now, why do we use vacuum in a rotary evaporator? Those rotary evaporators may run without any vacuum. Yes, as long as you manage to create enough heat in the water bath to cause evaporation on your sample. But with vacuum attached, you're way more flexible. There are way more options for your application. At the one hand, you can work at lower temperatures compared to a typical atmospheric distillation. And on the other hand, you increase your application range because now you can work even with high boiling solvents. Because under reduced pressure, those high boiling solvents evaporate at moderate temperatures. So, the vacuum in the process leads to increased process performance, reduction of the boiling temperature, therefore also the protection of possible heat sensitive samples, and it saves you also energy because you don't need very strong heating anymore. And it is reducing the steam generation from the heating bath. Now, the job of the vacuum pump here is to establish and maintain the process pressure. And that's important to cause the evaporation initially. And then also after causing the evaporation, to keep the pressure at constant rates throughout the whole process. And therefore also guide the whole process, because the vacuum needs to adapt to the pressure that is generated by the changing parameters throughout the process run. But we will come to that later in more detail. Now let's look at the topic of an optimal setup, of optimal conditions, starting with the temperature, because also crucial for high efficiency and short duration of evaporation processes is a large temperature difference between bath and solvent temperature, as well as between the solvent temperature and the coolant temperature. These differences should be about 20 degrees each. If, as in this example shown here, the solvent should evaporate at 40 degrees, which is usually also the temperature we know from the classic boiling point tables. I mean, these tables are usually laminated next to the Rotary in the classical chemistry lab and indicate the corresponding pressure ranges in which the solvents begin to boil at a certain temperature, most likely 40 degrees. And now that the target temperature of the heating bath, we wanna heat up our solvent to 40 degrees, so the target temperature of the heating bath should therefore be set to 60 degrees, so 20 degrees higher. And the temperature of the coolant should then be 20 degrees, so 20 degrees lower than the temperature in our flask. And normally the coolant temperature is assumed because we use classic water cooling. But when using a recirculating chiller and a colder coolant, like example something that reaches about 5 degrees, the other temperature specifications can be corrected downwards accordingly. Now to the second point, the vacuum control. And a big question that is always coming up with this topic. Do I need vacuum control, or do I just run an uncontrolled process? And sometimes there is this opinion that an uncontrolled process would run faster because there is this massive power of the pump and the maximum suction speed that removes all the vapor from the system in an instant. Well, that is not the nature of the rotary evaporation. It is needed. It's indeed a very balanced process. Like I said before, you have the evaporation and the condensation, and those processes should always be in balance to have a very optimal, very efficient process. So it's not always, also here the phrase, the more the better, the faster the better, right? No, it's control that gives us the efficient process here. The optimal process pressure, is not the lowest pressure, it's the actual vapor pressure of the solvent under your specific process conditions. And this vapor pressure actually changes throughout the process. Because on the one hand, when you think of evaporation in your flask, on the one hand you constantly change the mixture in the sample flask because of this evaporation, because the concentration and composition of the mixture changes with every distillated drop. And on the other hand, there is this constant change in sample temperature through the heat loss coming from the evaporation. Because the transfer from liquid into gaseous phase costs energy, and this energy is taken out of the heat, from the heat of the sample temperature. And that can never be completely compensated from the energy coming from the water bath. So, looking through the process steps of a very good rotary evaporation, in the first phase you need to find the right process conditions and adapt the pressure to the right vapor pressure of your solvent. And then when you found that pressure, most likely is exactly the pressure that is given in those tables on the side of a rotor. And in the second phase, then the very important phase now to have this very efficient process. In the second phase, you then need to continuously adapt to the changing conditions and follow the actual vapor pressure in the system. So you reduce your system pressure step by step, and you're not holding it at a certain level. The first level you witnessed evaporation. No, you have to go down with it by time to adapt to the actual vapor pressure that is in your system right now. So, to come back to the question at the beginning, controlled or uncontrolled processes. Here we can definitely say controlled processes will always be better and more efficient because you can operate in the equilibrium, and this is the efficient way of doing so. But that leads to a second question. Should the vacuum control work manual or automatic? Do I want to adjust the whole setting by myself and so babysit my application? So that's obviously the manual control. Or do I give the process responsibility to a vacuum system that will guide the whole process for me automatically, and I can do other stuff in the meantime, like writing my lab journal or doing some other stuff in the lab? And to answer this question, let's have a deeper look into these two possibilities. First of all, when we talk about manual vacuum control, it is usually the two-point control showcased here. Here you put a solenoid valve inside the suction line between vacuum pump and application. In this showcase, it's obviously the rotary evaporator. And that solenoid valve will then regulate the vacuum by opening and closing. But due to that switch point of the valve, you have the so-called hysteresis. This little pressure fluctuation that we can actually see in the graph above, that is this characteristic zigzag line that is in our pressure to time graph here. So, nonetheless, we still have a reliable process control here. That's very important. It's still reliable, but it's not perfect. It is, with this setup, also even possible, and that's very special, to supply several rotary evaporators with a single pump. And for this special and also space-saving application, we also have special pumping units in our product portfolio. Now, the biggest difference to the automatic control, however, is that no uniform distillation is possible. Because we will always have hysteresis fluctuations at every pressure point. So every pressure point we set, we will have this zigzag line throughout the pressure holding process. Furthermore, with this type of vacuum control, we would have to monitor the application frequently so that we can adjust the vacuum set point to the changing process parameters as mentioned before. So in other words, we need to babysit the whole process if we want a very efficient one. And now obviously the more comfortable way of doing so is the automatic option. And here the best way when going is when going with a speed control version. In the vacuum brand product range, you find the so-called vario systems. The term vario always indicates speed control. And here you have a RPM, so rounds per minute, controlled system in the background. So the motor speed is RPM controlled. And you also need an electric controller that adapts the actual operation of the pump to the requirements of your application. And this is all done in real-time operation, leading to a completely hysteresis-free pinpoint vacuum control. As we can see in the graph, we don't have a zigzag line anymore. We have a perfect and smooth graph. And this is therefore the highest vacuum control precision that is achievable right now. It leads to high process reliability and because of the reduced operation time, it maximizes service life of the pump. Then you also have the reduced power consumption because of obviously reasons. And when you ever heard one of these systems in real life, you will have noticed that they really work nearly silent. So, coming back to our question regarding the vacuum control, manual or automatic? Well, I think it's obvious by now, but let's take a closer look to it. And now let's have a look back in our testing laboratory studio and watch another short movie in which we showcase the automatic process for you. Well, here you could see how the various system takes full control of your process and automatically adapt to the changing conditions. And on this slide now, you can see the pressure curve, pressure against time of such a run we just showcased in the video. First, there is this boiling point detection in the process, which is done very precisely in order to prevent any undershooting of the vapor pressure that would eventually lead to foaming or bumping in the evaporator flask. And so here the system works very sensitive and precisely to detect the first boiling point. But from there, once the evaporation has started, you have this continuous change of process parameters through, as I told you before, the heat loss and the changing concentration of your mixture. So, normal 2-point controls where I set the vapor pressure to a certain vacuum level, I set the vacuum level to a certain vapor pressure, then I achieve this pressure, the evaporation starts, and then I hold this pressure. But that's not the effective way of doing so. So from here the system goes, the automatic system goes in some kind of tracking mode in which it step by step follows these changing conditions in real time until the end point of the evaporation is achieved. So we are lowering the process pressure by time to adapt to the changing conditions. And the automatic does this all by itself. And if you now have, think of a manual control, like the classic 2-point control, you need to babysit your application because you need to change the vacuum level by yourself, so you can adapt the pressure by yourself. And the automatic here does the job alone and all by itself. And if we take a look on the right hand side now, we have another graph. We can see the energy consumption in such a process run, comparing the speed controlled various system in blue underneath with the classic 2-point controlled fixed speed system in red above. And here we observe the evaporation of ethanol. And the visible, obvious takeaways from it are that the process time of the various systems is shorter and the energy consumption is significantly lower than the fixed speed systems. So now let's take a closer look at the ideal control panel for the whole topic regarding vacuum control. And this is our current vacuum controller, the Vacuum Select. It is very user-friendly and also has a touch panel that is simply operated by icons. And now regarding the Rotary evaporator, for this we have an already pre-installed program on the vacuum controller, the so-called automatic evaporation. So this is the program we were talking about the whole time when we talked about automatic mode. And this program keeps the process of evaporation in an ideal equilibrium, exactly as I have described it before, to have a very, very efficient process. And if required, however, this program can be further modified by changing certain parameters, as seen here on the right. For example, the sensitivity of the detection of the vapor pressure can be adapted from low to normal to high. But we will come to that in the best practice example on the next slide. And if necessary, you can also set a value, a pressure value, for an intermediate stop to empty the collecting flask for solvent mixtures with high and low boilers in it. So if you have high and low boilers in your evaporation flask and you want to change them, you want to separate them because you want to have a clear separation, and you know, okay, my high boiler will not start evaporating under like 10 millibars, then you can put this intermediate stop at a certain pressure range, and therefore have a clear cut, a clear separation, enough time because the pump will stop to change the flask and then start the process from new. And now I would like to present you an example of our best practice. To do this, we carry out a thought experiment, which involves the evaporation of milk. Milk, as most of you know, is a very sensitive media when it comes to the evaporation, because it has a very high surface tension and therefore leads to heavy foaming. Most of us will know this behavior from our own kitchen, where we made our own experiences with it when overboiling milk while heating. Terrible, the whole stove is ruined and the milk is also ruined. So everybody knows a solvent with also these characteristics. So just think of a solvent if you don't want to think about milk. And for sure, most of the people that work in the lab will have such problems with certain solvent mixtures or product mixtures. And now our various systems are even capable of handling even such sensitive media. So, and to realize that, it should be obvious by now that we set the sensitivity of the boiling pressure automatic, the one auto mode we talked about earlier, in our editor to high. But this also means that the pumping unit works very slowly, very precise, in order to make sure that no undershooting of the vapor pressure is happening. And this may lead to relatively long process times if started from atmospheric pressure. And our Vacuum Select controller allows us now to speed up the process, and that with the help of the editor mode. we can use the editor of the controller, and therefore we can add several steps in a row. This allows us to run a pump down process to a certain vacuum level before the actual boiling point detection even starts. This step takes place, so the pump down mode then takes place at maximum speed, and the automatic boiling point detection only starts afterwards when achieving this certain vacuum level. This means we can pump down from atmospheric pressure to 70 millibars in a very fast fashion, and then only the automatic boiling point detection with a high sensitivity will start and find the vapor pressure precisely. So, we can present you a very useful tool to combine different process steps in one program for your individual needs. Now let's summarize the optimal working conditions for the rotary evaporator. First, you have to make sure that the entire system you're working with is leak tight. For that you can run a simple leak test that can be happening like weekly or monthly. That's up to you. Then start the vacuum control either with a set point of vacuum or in the automatic mode if possible. And first then immerse the evaporating flask in the heat bath. For the temperature control, just follow the delta 20 rule, the delta 20 rule. And yes, very important, as I said before a few times, put evaporation and condensation in an equilibrium. But when working with a automatic mode, that's no problem, because the pump, the vario pump, will do all the thinking for me. I don't need even to stand by the whole application, so no problem. But what is when we operate our process manually, when we have to find this equilibrium by ourselves? Well, there is actually a trick there for it. There's a visible point on the condenser you can check. And you look at the condenser and you look at the condensation on the condenser, and if it's about 2/3 of it, so if 2/3 of the condenser is wet and dripping, then we can be pretty sure that our process works in an equilibrium. So, easy check, just look at the upper third of the condenser. If it's dry, you're good to go. Then always set the pressure correct when working with the vacuum controller. This especially is important for the 2-point control, and is very important for the hysteresis, that the hysteresis is chosen correctly. Otherwise, there will this constant and frequent switching of the valves, which is on the one hand very annoying for the acoustic, for your ear, and also not good for the longevity of the switching valve. So a rule for the hysteresis is always like 10% of the value of your current pressure that you of the current pressure set point you set. And last but not least, check the ratio of the solvent quantity in the collecting flask of the condenser, and also check the quantity of the solvent in the round flask underneath the emission condenser at the end and the outlet of the pump or pumping unit. Very important step. So we are slowly coming to the end. Now that we have heard a lot about vacuum basics and the correct way to work with it and to work with the rotary evaporator in all the vacuum ranges, the final question of this webinar is, of course, what is the right pump for my individual application? So first of all, choose the application you want to work with, then define the process parameters, like with what kind of media am I working? Am I working with very aggressive chemical vapor, so I need a chemistry resistant vacuum pump, or is this not the case? And so on and so on and so on. So you have very, very, very much of parameters to clarify in order to find the right vacuum pump for your system. So is it easy? It's not that easy. However, there is a lot to consider and taking into account, and that's exactly why we have developed the perfect tool to make life easier for you. Our so-called vacuum pump selection guide. And all we have talked about is reflected here, meaning meaning that it is a selection tool which guides you through the whole process of finding the perfect vacuum pump for your individual applications. So at the end, it will guide you to the most appropriate system that is perfect for your specific demands. You can find it easily on our website vacuumband.com. And now is also the perfect time that I showcase ongoing sales action we have at the moment, that we are have some pumps in stock at sale that are very suitable for the Rotary evaporator. So if you have any needs, check our website and look for the good sales deals. So we are now at the end of the webinar for today. Thank you very much for your interest in this topic and the attendance. And if there are any questions left now, I will try my best to answer them. Thank you very much.
Thank you, Florian. We indeed have a question from the audience. Here's somebody working with light-sensitive solvents. So the question is there a possibility to work protected from light and still control the process?
If you have an automatic mode, that is. So I also worked with in the past with very light-sensitive components, and we always wrapped our whole rotary evaporator in some kind of dark shade, so no light was coming through the glass. But that means that you can use the trick with the condenser to look for the equilibrium. So you either run a not perfect process, which is totally fine because you still get the distillation done at the end, or you have an automatic pump like the Vario pumps, and then you don't even need to think about it. Start it, have the automatic mode active, and just wrap up the rotary evaporator like with some kind of material to protect it from light. And there are also special glass flasks that suits the rotary evaporator that are like in a brown color that protect also light from destroying your special product mixture. So that would be my try to solve that problem. It is possible. It is a lot of work to do because you need to wrap it up and look very safely to it and run some test runs to assure that everything works fine. But I think it is actually possible to do so.
We have no further questions. Thank you, Florian. Thanks everybody for joining us today.
Thank you very much.